Hello everybody and welcome to this video. This is going to be the serving in place of the lecture for Tuesday, November 15. What we're going to do is follow along with this note sheet. This is one that we started on last Tuesday's class. So we're going to go through this kind of briefly. I have some parts already filled out, so what you're probably going to want to do is have your note sheet out and then be pausing the video at different points to make sure that you're catching everything and that you're able to fill out stuff. But hopefully this keeps the video time down a little bit and gives you a chance to work through it at your own pace. I have the first part filled out, but just to kind of remind yourselves what we're looking at switching from control volume analysis to control mass. So a control volume, we have stuff flowing in and out of the system. A control mass, we're looking at one group of stuff, say like 1 pound of steam as it's traveling through a system. So we're starting here with the difference between point functions up here and path functions. Point functions, what we have are functions where the magnitude depends on a specific state. So the types of things that we could look up in our tables, right? T, P, H, U, S, but also things like kinetic energy here and potential. A path function is a different type of function or a different type of thermodynamic variable, something that depends on the pathway, depends on the process. So we're talking about something that starts at an initial state, ends at a final state, and the value of this matters which way we go. So things like heat, Q, and work are both path functions that we've been dealing with. So we've usually been writing the law of thermodynamics. This is, again, the first law for a control mass, writing the point functions on one side of the equation, the path functions there on the other side of the equation. Right? We're dropping kinetic and potential energy, and we're swapping out H for U, again, because of this here. H included both thermal energy, U, and also flow energy. Because we're in a control mass framework, we're not looking at flow energy, so the only energy that we have is the thermal energy, is the internal energy, U. All right. So this problem, we started in class, we got part of the way through. You'll probably need an extra piece of paper. I don't think I gave you quite enough room here. So maybe rip your packet apart and insert an extra piece of paper here. But at this stage, we're going to kind of dive in and go through actually solving this problem. Right? We're going to solve this problem. Again, 100 grams of steam. We're starting at this initial state, and then we're ending at twice the initial volume and a final pressure of 400 kPa. So we're going to do 3 different paths between that initial state and the final state. We're going to solve primarily for work. In the first example, we're going to solve both for work and for heat transfer. But then in process 2 and 3, we're just going to be looking at the work. All right, so if we dive in here, we have a lot of this done already for us. So first what we're going to do is draw out the process, something like what I have up here. So maybe you want to pause and take some time to do that. Take some time to copy down these key equations. So those are equations that we're going to be using really throughout our analysis of control masses. We have an equation here at the top where we can directly calculate work. And we have this equation that we've used before at the bottom where we can directly calculate heat transfer. We can only use these equations if we can actually solve the integral. So we'll see some places where maybe that's easy, some places where that's a little bit more challenging. In this particular process, we have first a constant pressure reversible process from 1 to 2. Then we have a constant volume reversible process from 2 to 3. We can look up, because we know temperature and pressure, we can look up everything for state 1. We can then go ahead and calculate the volume for state 2. Again, we did this in class, 1.593 meters cubed per kilogram. And that allows us to look up the internal energy, which is 3594 kilojoules per kilogram. We can look up then, again, the pressure, using pressure and volume, we can look up internal energy now for state 3, which would be 4273 kilojoules per kilogram. To solve the work, we're going to do that step by step. So we'll first look at the work for step 1 to 2. We're solving this equation here. We can pull out pressure out front of the integral. We can also pull mass out front of the integral, right? P and M are both constants, so they can both come out of the integral. That is only true for this special case. It's only true if they are actually constants. Mass is typically going to be a constant because we are looking at a control mass, which is really by definition a single amount of stuff. But pressure is not always going to be constant. So this equals mass pressure times the integral from 1 to 2 of dV, which is just equal to mass times pressure times delta V, or 0.1 kilograms times 300 kPa, which is our pressure, times the change in volume, 1.593 minus 0.7964 meters cubed per kilogram. Right, a note on units over here. A kilopascal is a kilojoule per meter cubed, so we have kilogram times kilojoule per meter cubed times meter cubed per kilogram. So kilograms will cancel out, meter cubed will cancel out, and we'll have units of just kilojoules. So our work becomes 23.89 kilojoules. We can then find our heat transfer using a simple energy balance. We have delta U equals Q minus W, or we could rewrite this as Q12 equals delta U plus W, just by simply rearranging our equation. So we can find Q, capital delta U is the mass, 0.1 kilograms, times the change in internal energy, 3594 minus 2729. So we're still doing, instead of out minus in, it's final minus initial. Those are in kilojoules per kilogram. So those will work out to be kilojoules per kilogram times kilograms, just kilojoules, plus our work, 23.89 kilojoules. So we can then calculate Q12, which is 110.4 kilojoules. That's the first step in our process. We can then move on to the next step, step 2 to 3. So step 2 to 3, and again here you may want to pause a little bit to make sure that you can catch up. But step 2 to 3, we don't have a change in volume. So this was the step that by definition was constant volume. So we have a constant V, which means W is equal to 0. So we only get work if we have a change in volume. So that's one of the things that we learn as we start to evaluate control mass problems. We really need an expansion or a compression. We need this change in volume in order to extract work out of the system. Basically, our fluid needs to be either pushed and change volume or push against something and change volume in order for work to be put in or to be extracted. So we can solve then for Q. Same basic thing, so we can write the total energy balance here at the top, and then we can rearrange that. We have the same mass. Our delta U is now final minus initial, so it's our final U, 4273, minus 3594 kilojoules per kilogram, plus our work, which is 0 kilojoules. That leads to our calculated Q on this step of 67.9 kilojoules. If we wanted to find the Q for the entire process, we would add these together. If we wanted to find the work for the entire process, we could add our two different works together. A helpful way to think about this, though, is on a pressure volume diagram. So when we were looking at CVs, we often did a temperature entropy diagram. That was fairly useful. Those are also useful in these problems, but pressure volume diagrams are too. So we'll see why in a second. If we look at this PV diagram, I already have labeled the volumes relevant here at the bottom and the relevant pressures here on the left side. I've already put our initial state and our final state on the graph. So for this particular process, our first step is a constant volume increase in pressure. A constant pressure increase in volume. So we're going this way from 1 over to 2, and then we hit, right, if we scroll up. So this first step here, the volume is changing, but the pressure is not, right? Pressure is 300 and 300. In the second step, 2 to 3, we have these little stops here, which are stopping our piston from moving any further, so it's keeping us at constant volume. Okay, so our second step here, we have a straight vertical line then between 2 and 3. We can visualize the work in the system as the area here under the curve. So the work of the process is just the area under the curve. And that's why we like this type of visualization. So let's move on to the second different process. So again, I have a lot of this stuff already drawn out. So we have an initial state, which is 300 kPa and 250 C. It's the same initial state we had before. Erase this. So we have the same initial state here and the same final state. So we already have the final state, so we can just write down what we already know about it. So our final volume was 1.593 meters cubed per kilogram, and we already looked up our final internal energy. It was 4273 kilojoules per kilogram. I've already placed those then here on the right hand side on our pressure volume diagram. So you can see, right, those are already over there on the PV diagram. In this particular case, we have two different processes. So we're first heating at constant volume, then we're heating at constant pressure. So you can imagine we're heating up here, constant volume, until we kind of let the piston move, and then the second process we're heating at constant pressure. So we're coming here in 2. Our volume is not changed, so it's still 0.7964 meters cubed per kilogram. Then we can look up pressure and volume with, say, something like Cat3 or in steam tables, and we can find our internal energy of 2997 kilojoules per kilogram. Then we can calculate work. The work for this initial step, right, between 1 and 2, between 1 and 2 we don't have a volume change. So same thing that we had before. Between 1 and 2, work is equal to 0, again because we have no volume change. Between 2 and 3, we have the same equation. We have a constant pressure. Here between 2 and 3, pressure is not changing, so that allows us to simplify our integral equation down to simply something like this. So we can say this is 0.10 kilograms, our mass, times our pressure, which is 400 kPa, times our change in volume, which is 1.593 minus 0.7964 meters cubed per kilogram. And if we plug that into our calculators, we get a work of W23 is 31.86 kilojoules. If we want to visualize that, here on our PV diagram, you can zoom in here. In this case, we're going up in pressure first, from state 1 to state 2, and then we're staying at constant pressure and increasing the volume. Our work is again the area under the curve, and change colors. So our work is again this area. You can see there is no area under the curve between 1 and 2 because it's a straight vertical line. So that doesn't have area. So the only place that we have an area under the curve is between 2 and 3. So this is the work. And that's, again, why we like PV diagrams, because it really shows us clearly the area under the curve is equal to the work. We can also see how different pathways, like this one, results in more work because we're going up first and then we're going over to the right. So we have a larger area underneath that curve. Okay, third different process. What we have here is an expansion between 1 and 2, where we have a linear change in pressure. Right, so what we can kind of imagine is we have a spring that's on the piston, and now that spring is all bunched up. So that's sort of physically what this might represent. We can write, because we've already done this before, we have the same initial state, the same final state. So we already know what volume is, we already know what internal energy is of the initial state and of this final state. Again, they're the same that we had before. If we go over to the PV diagram, we already know what the initial state and the final state looks like. In this case, it's 1 and 2 because we don't have an intermediate state. This is just a one-step process, and we could already draw what this process looks like. It's a linear change in pressure as we're increasing in volume. We could also already draw the work for the system. We'll use that in a second. All right, so the equation that we're actually trying to solve now, we're actually trying to solve this equation here. Work is mass times the integral of PdV. Now, there's more than one way to solve this. We can't just pull pressure out of the integral because pressure is not constant anymore. It is changing. We have a change between 300 and 400. We also have a change in volume, so this is not equal to 0 as it was before, where we didn't have a volume change. It's actually a change. We have to consider that. One of the ways that we could solve this is by finding a function of p. So what would that look like? So it might look like something like this. So pressure equals 300 kPa plus 100 kPa times basically how far are we between the two different volumes. So something like V minus 0.7964 divided by 1.593 minus 0.7964. So looking maybe a little bit like linear interpolation. This would give us a function of P as a function of volume. We could then insert and integrate. This would work fine. We're eventually going to do things like this, but for this particular problem we can simply solve it graphically. We know that the work is, as you can see in the graph on the top right, the work is just the area under that curve. So we can use simple geometry to be able to do this. So work is equal to the area under the curve on our PV diagram. All right, so how do we calculate the area of that shape? We go back to high school geometry class, and we can write that the work is equal to the kind of the midpoint pressure times the base, right? The middle of the height times the base. So 0.1 kilograms, that's our mass. Now times 300 kPa plus 400 kPa divided by 2. Now times our base, 1.593 minus 0.7964 meters cubed per kilogram. And we can find that the work is 27.87 kilojoules. So this is one solution where it really helps to be able to know that the work is just the area under the curve on a PV diagram. Right. Turning to the last page, we're going to do two more quick problems, again just to show how some of the things that we've done before, the energy balances, the types of analyses we've been doing, will translate largely from control volume problems to control mass problems. So in this case, we're going to imagine applying the second law. So the second law works for control mass problems just like it does for CV problems. So if we have, for example, an adiabatic reversible process, we know delta S equals 0, something that we've done a bunch of times now. That will still be true. If we then have some process like this, so let's say we have an initial state, 500 kPa and 350 C. So we've shown that, this initial state down here. If we look at now that expanding reversibly in a piston cylinder apparatus, and we know that the process is adiabatic, we can determine then the work done per kilogram of steam. All right, so how would we do that? We know our final pressure is 100 kPa. So we wrote 100 kPa there as our final pressure. We know that the process is reversible and adiabatic. So just like for CV problems, we're instantly thinking delta S equals 0, or S2 is equal to S1. So we can write that S2 is equal to S1 is equal to something that we'll look up here in a moment. All right, so that's great. We can then look up pressure and temperature. If we do that, say in Cat 3 or your steam tables, we can find that U is 3128 kilojoules per kilogram, and S is 8.087 kilojoules per kilogram Kelvin. Because we know that the S of state 2 is the same as state 1, we know it's also 8.087 kilojoules per kilogram. Then what we can do is take that pressure and that entropy and look up what the final internal energy is. So U2. So U2 is 2756 kilojoules per kilogram, and we don't need this, but just for the sake of seeing it, this is 154.2 degrees Celsius. So this is an adiabatic expansion, just like expansions that we've encountered before. As we're expanding to lower pressure, we're also going to lower temperature because we're extracting out, right? We're taking the thermal energy that we had, extracting out some of it. Okay, we can solve then for our energy balance here. This would be the energy balance for our control mass system. We know already that it's adiabatic. That means Q equals 0. So then delta U equals minus W12, or mass times delta U equals minus M W12. Our M's can cancel out and we get delta U equals minus W12. Again, the same as what we've done before if this had been a control volume problem. The change is that we've switched from talking about enthalpy or H to now talking about internal energy or U. We can plug in our numbers, out minus in, or final minus initial in this case. 2756 minus 3128 kilojoules per kilogram equals minus W12. So W12 is equal to a positive 372 kilojoules per kilogram. So when we have an expansion, that's when we're going to be getting a positive work out of our system. So to compress it, we're putting work in. When it's expanding, we're getting work out. Again, same as what we would see for a control volume process. We can continue and do another thing that we've done before, which is solve something with a device efficiency or an expansion efficiency of 75%. We'll continue to assume this is adiabatic. So if we have something here, now the efficiency is 75%. This is still equal to W real over W ideal. Same as what it would be for, say, a turbine, an expansion, a work generating process in a control volume problem. We do the same steps. So step 1 is solve the 100% efficiency. Right. The good news is we just did this. It's right up there. So W12 ideal is equal to 372 kilojoules per kilogram. We can then use efficiency in step 2. W12 real is 0.75, so 75% of the 100% efficiency thing. So 0.75 times 372 kilojoules per kilogram. And we can find our real work, which is 279 kilojoules per kilogram. Again, hopefully this feels familiar. It really does behave exactly like what you would expect it to behave like. We could then, in step 3, if we wanted to learn about the state, the actual state 2, we could go back to our energy balance. So we could find our real outlet, with an equation something like this. So it would be U2 real minus U1 equals minus W12 real. And then we could use that to find, what's actually coming out, what's actually the final state of this expansion process. All right, so that's going to be the end of this video. That's the end of this week's class. Make sure you go through and fill this out. There is a homework that is due Thursday. It's a couple problems a little bit like this. Hopefully they go fairly smoothly. You're also remembering for Thursday the take-home exam. So both of those things are due Thursday, and I look forward to seeing you then.